Okay. Good morning, everyone, and welcome to the second session of our 2-day spanning international seminar on atmospheric chemistry, recent highlights. So from today's presentation, now we know that atmosphere is a complex and extremely large reaction space where hundreds, if not thousands, of parallel and competing reactions are taking place at the same time. So given their immense impact on life forms, they need to be understood in detail. Besides experimental techniques that we learned from yesterday's presentation, advances in physical and chemical insights and computing resources have led to advances in atmospheric chemistry too. Today we'll hear from Dr. Bandyopadhyay from MNIT Jaipur about that other side of the atmospheric chemistry. Before we go into the core section of the seminar, I request our principal to say a few words. Dr. Bandyopadhyay happens to be our alumnus, so just say a few words before we start formally the presentation.
सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः हरिः ॐ. Respected Vice Principal Maharaj, who is present here in the webinar, respected Professor Biman Bandyopadhyay, Head and other members of the Faculty of Chemistry, beloved students, my respect, good wishes, and namaskar in due places. As we have already heard, Professor Bandyopadhyay is an ex-student of this institution, so I need not give any introduction in that sense. Just to remind myself, the Holy Mother, as Thakur used to say, great master used to say, was the embodiment of Mother Saraswati. So the inculcation of knowledge, that has been the very spirit behind running these institutions, educational institutions run by Ramakrishna Mission, and all along the journey traversed by Ramakrishna Mission Vidyamandira in the last 79 years, we have tried to maintain that spirit. And even in this COVID scenario, when the whole educational system is in turmoil, we are happy to see that the Department of Chemistry, along with all other departments, actually all the departments have been organizing such webinars. So today's webinar is definitely going to be an important addition to that. I do hope and pray to the Holy Child that it becomes a great success, that it was the case in the earlier webinars as well. Once again, I welcome Professor Biman Bandyopadhyay and do hope that he comes to Vidyamandira when situation becomes normal. Om Shanti 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 Harihi Om Tat Tat Shri Ram Krishna.
Thank you, Maharaj, for your warm wishes and invitations. We also have our Vice Principal, Sami Mahaprabhanandati, in our virtual studio. We heard Maharaj give some insights from his biology background about the acetone in the atmosphere today. So today our speaker will be specifically talking about ammonia, which is more relevant, I think. So I will request our Vice Principal to say a few words before we start on the formal presentation.
Thank you, Anirban. So a very good morning to respected Dr. Biman Bandyopadhyay, today's distinguished speaker. My love, best wishes and respect to all the faculty members of Department of Chemistry, including Brahmachari Ishatma Chaitanyaji Maharaj, and my humble salutation to revered Srimad Swami Ekochittanandaji, Principal, Ramakrishna Mission, Vidyamandira. Yes, as rightly pointed out by Anirban, being a student of biological science, ammonia quite naturally gets our attraction. it is not only that ammonia occurs naturally and it is found throughout the environment in soil, air, and water, but ammonia also renewed very naturally as a part of the nitrogen cycle and already occurs as plant for as fertilizer. It is a very prominent source of nitrogen, which is one of the essential components in the soil. And as a result of this natural process, ammonia does not last long in the environment and it also does not bioaccumulate. And as far as fertilizer industry is concerned, the data available, about 90% of the ammonia produced, it is used in our fertilizer and to help sustain food production for billions of people across the globe today. And we know ammonia can also be used to clean a variety of household surface regularly, from our tubs to sinks, our toilets, kitchen counterparts, tiles, everywhere. And interestingly, when it is used as a refrigerant gas and in AC, air conditioning equipment, ammonia is a very good absorber of heat. It can absorb substantial amount of it from its surroundings. And from the standpoint of water purification, ammonia is also used to purify water supplies as a building block, and as a building block in the manufacture of many products, including plastics, some explosives, sometimes fabrics, pesticides, dyes, and so on. And it is also used in the wastewater treatment, cold storage. So it is multifaceted application, and it's a very fascinating gas in that sense. Now today, I find is very relevant that Professor Bandyopadhyay will enlighten us more about the environmental chemistry of this wonderful, important gas today. So once again, I congratulate the faculty members of chemistry department for arranging wonderful webinar, and thank you everyone, and I request to initiate today's session.
Well, thank you, Moraj. Indeed, ammonia is a very important chemical that has immense impact on our life and all other biosphere. Dr. Bond, we are really excited to hear from Dr. Bandyopadhyay. So, yeah, he is an alumnus of Vidyamandira, but he has a lot more than that. So I'll request the convener for this seminar, Dr. Riaz, to introduce our speaker to the audience. Dr. Riaz. Hold on a second, he was just there and got disconnected. Can we have Dr. Riaz back in the studio?
I think I am back.
Okay, thank you.
Can you hear me?
Please
Okay.
introduce our
Yes.
speaker.
Yeah. I understand. Thanks, everyone. I am particularly thankful today for the opportunity to introduce the speaker of the current session, Dr. Biman Bandyopadhyay, as he happens to be an old friend of mine. As Anirban mentioned, Dr. Bandyopadhyay is an alumnus of this college. He graduated from here in 2003 before going to Kanpur IIT for his masters. Dr. Bandyopadhyay did his PhD under the supervision of Professor Taposh Chakraborty at ICS. Later, he received D.S. Kothari Fellowship for postdoctoral studies. Finally, in 2015, he joined the Malaviya National Institute of Technology, Jaipur, as an assistant professor in the Department of Chemistry. Now, during the initial phases of his career, Dr. Bandyopadhyay was focused on studying the behavior of tautomers and dimers using matrix isolation infrared spectroscopy. Later on, he would explore newer avenues, and currently he is also engaged in theoretically studying organic reactions in the upper atmosphere. The topic of his today's presentation has to do with this particular branch of chemistry. Specifically, he would be dealing with atmospheric chemistry of ammonia, its impact on gas phase hydrogen transfer reactions. Now, may I request Dr. Biman Bandyopadhyay to start his session.
Thank you, Dr. Riaz, for the kind introduction. And before I start, I would like to thank wholeheartedly to Jit Maharaj for giving me this chance to attend this webinar and present my work here. And all the faculty members of chemistry department, Principal Maharaj and Vice Principal Maharaj. Okay, it is actually kind of a homecoming for me, albeit virtually. Maybe later on, as things will improve, I will be able to go back to my alma mater in sooner rather than later. Now, hello. এখানে লাইটের প্রবলেম আছে একটু। Now coming back to the topic, I'm going to talk about atmospheric chemistry of ammonia, impact on gas phase hydrogen atom transfer reactions. But before starting, it is better to understand what I'm not going to talk about, because as Vice Principal Maharaj already said, that the chemistry of ammonia is very expanded. It actually encompasses the biosphere, the geosphere, the atmosphere, almost all aspects of terrestrial life and terrestrial chemistry. Okay, so we are going to talk about only the atmospheric part of ammonia. Even if you go to the atmosphere, then what happens is that ammonia has a very wide range of chemistry. It actually means its most important till date known chemistry is actually heterogeneous chemistry, because it helps in formation of secondary organic aerosols by reacting with various SOx, that is sulfur oxide families, and NOx, that is nitrogen oxide families. We are not going to talk about that as well. We are going to specify that we are going to talk about only gas phase chemistry of ammonia. And moreover, in the gas phase chemistry as well, ammonia can participate as in different types of reactions, but we are going to talk about the hydrogen atom transfer reactions only, a specific class of reactions. Now, the way atmospheric chemistry works is in this way, because the atmospheric chemistry is such a vast subject. There are so many different types of processes going on, physical and chemical, that for one person or for one research group, it's impossible to encompass all of those things. So what we do is that we normally take it like a jigsaw puzzle, and we try to fill in the different small parts according to our own capabilities, and try to find out what the whole picture is. So as we go in, I will like to talk about the ammonia in atmosphere. Then we'll talk about atmospheric hydrogen atom transfer reactions, then ammonia in hydrogen atom transfer reactions as catalyst and reactant. Then we'll talk about methodologies. Then I will present some representative works of our group, and we'll talk about the future scopes of the scenarios. So ammonia in atmosphere. But before we go to the ammonia in atmosphere, let us go back and see the history of ammonia, how old it is. Now, before I started with ammonia, around 5 years ago from now on, I didn't realize that the history actually goes back to a very old age, even before the birth of Jesus Christ. The first mentioning of ammonia in written history is actually in the first history book that was written by Herodotus. Interestingly, what happened is that in that book, where he goes on to saying that of these nations, the first is that of the Ammonians, who dwell at a distance of 10 days' journey from Thebes. Actually, here he uses the term Ammonians, or rather, at that time, Ammonians were used to represent a certain race of people, not a chemical compound. Now, if we fast forward around 500 years and come to the 1st century AD, it was 5th century BC. Herodotus was in 5th century BC. Now, if we come to the 1st century AD, we find that Pliny the Elder, in his magnum opus, this Naturalist History or the Natural History book, he says about something called ammoniacum, and he says that by the production of ammoniacum, a salt called from the fact that it is being found beneath the sands there. So in 500 years, this ammonia becomes a salt from human. And then if we fast forward a little more faster, then we find that in 1756, Joseph Black first isolated the gaseous ammonia. Then Barthollet gave us the chemical formula in 1785 AD. And around 100 years later, Henry Louis Le Chatelier gave his famous equilibrium law, which we know as Le Chatelier's principle. And that actually paved the way of synthetic ammonia. In fact, Le Chatelier started working with ammonia, started working for synthesizing ammonia. But what happened is that there was an accident in his lab, and 2 of his lab workers almost killed themselves. Because you know that this reaction requires a very extreme condition, high pressure and high temperature. So after that incident, Chatelier shut down his project on ammonia synthesis, and then Fritz Haber came into the picture, and the picture completely got changed. So Fritz Haber tried for several years. Initially, he was a thermodynamics person, so that actually helped him a lot. And he finally found the way of synthesizing ammonia first time in 1909. The date was, I think it was 2nd of July. Okay. And the first time he reported that he got around 80 grams of ammonia in his lab. He used a catalyst which is not the iron-based catalyst that is used for industrial purpose, but that was osmium-based catalyst. Then in 1910, Fritz Haber joined with Carl Bosch, a very ingenious engineer, who devised a way of synthesizing ammonia at an industrial scale, and they filed a patent in 1910 AD. And 3 years later, BASF is a very chemical giant of Germany. They started mass producing ammonia, and the first plant they built up was having a capacity of 30 tons a day. And that was actually a point of no return, because from then on, everything started changing so rapidly, and we do not know as yet whether there is a way back to the pre-1940 condition. Let us see how these things changed. In 1920, when Fritz Haber gave his famous Nobel lecture, he concluded the lecture in a very prophetic manner. He said that let it suffice that in the meantime, improved nitrogen fertilization of the soil brings new nutritive riches to mankind, and that the chemical industry comes to the aid of farmer who, in the good earth, changes stones into bread. Now, this bold part is actually means having a reference from Bible, where Satan comes and challenges Jesus to prove his divinity by changing stone into bread. Jesus actually denied Satan. Here, Haber didn't deny. He literally changed stones into bread. And we find that how prophetic his words were that when he said this in 1920, around 30 years later, we find that there is a large change, rapid growth. If you look at this left curve, it is around 1950. After the Second World War is over, the industries are now starting to boom and bloom because the economic recession or depression, the Great Depression of 1930s is gone, the Second World War is over, the whole world is rebuilding, and people need food. So there were multiple fertilizer companies coming up using the same Haber-Bosch process, and we see that there is a rapid growth, that there is means literally a break in the graph. And if we look at the human population graph, we see that human population graph was a very steady graph, except if you leave that the Great Plague around 1350s ADs. But after Second World War, we see a similar break in the graph, as if you put these two graphs on one another, one will easily superpose. And if you look at the rate of the change of population, that rate of the change of the population, the rate also changes very rapidly in a region. It is not visible but please believe my word, it is actually in the region of 1950s. Okay. So the dream came true actually. Haber's dream came true, but it actually came with a side effect. What was the side effect? Ammonia is a very volatile molecule. So if you produce large amount of ammonia, larger amount of ammonia will go into the atmosphere. And as Vice Principal Maharaj said in the introduction section, that ammonia was used as a very good coolant before CFCs came into picture. So obviously what happens is that ammonia must be a very good greenhouse gas. So larger amount of ammonia going into the atmosphere has a cyclic effect. It increases the temperature of the earth, however small it may be, but it increases. And that increase will result in higher volatility of the ammonia. So if we look at the side effect, that is the ammonia in our atmosphere, we find that from the 1970s to 2005, this data I have, we see that there is a gradual increase of ammonia, and the different color codes that is given here, they actually give you the various sources of ammonia. We see that the largest source of ammonia is the yellow color coded, that is agriculture, emission from synthetic fertilizers. And we see that almost all the other sources like forest and grassland fires, energy like fuel combustion or transport, agriculture including the livestock manure management, and other sources, industrial processes, they do not change much over the time. The major change in the overall bar diagram is being contributed by this yellow graph, which is coming from the synthetic fertilizers. Okay, so if this is the scenario, we need to look ahead and find out what will be the scenario in the coming years, because we need to prepare ourselves. Why? Because as of now, we do not know a second way of producing larger amount of food for ever larger number of population, and we will have to depend for the foreseeable future on the ammonia-based fertilizers. So if we plot the ammonia means global ammonia emission, which is given in gigagram NH3 nitrogen. Just let me tell you, NH3 nitrogen means that this is actually not the amount of ammonia, but this is actually the amount of nitrogen. That means if here 14 gigagram is there, that means the ammonia will be 17 gigagram. So we see that the change is almost a linear change. And if we find out the equation, we find that there is a means y is equal to mx plus c kind of an equation. So if we simply extrapolate this linear equation in a linear form, we find that by 2050 the global emission will be around 7.6 into 10 to the power 4 gigagram, which is 76 teragram nitrogen, ammonia nitrogen. Just imagine that in 1970s it was only 2.5, and in 2005 it was only 5. So it is almost becoming 3 times if the prediction holds true. This is a very gross prediction. I'm accepting that. But if the prediction holds true, then we are looking into the global emission of ammonia reaching 3 times that of 1970s. So let us look at the global picture, how things pan out in different regions. So in 2016, Warner's group actually did a very good research, and they showed that how ammonia concentration is changing. They get this data from this AIRS detector, which was installed on an aqua satellite sent by NASA, and they showed us 4 different hotspots of ammonia. One is this Midwest US, one is this China, the second one, the third one is the Western Europe, and the fourth one is the Indian subcontinent. Now here the ammonia concentration in atmosphere is given as ppbv. All of us know what ppb is, that is parts per billion, but when you say ppb, we actually talk about number of particles, in terms of number of particles. But in atmospheric chemistry, normally what we do is that we express an abundance of any trace amount of species in ppbv, where this parts per billion is in terms of volume, and this is normally known as volume mixing ratio, which is expressed as VMR. So now let's look at the pictures. We see that according to this bar diagram, the maximum limit is 10 ppb, and starting from 0 obviously, and the red regions actually represent the vicinity of 10 ppb, and we find that it is actually this China and India which are worst affected. If we look at the condition of USA, we see that they register around 2.6% per year increment, and the reason for this ammonia concentration, increase in ammonia concentration or abundance, is twofold. One is decreased chemical loss. Chemical loss means that the ammonia that reaches the atmosphere, how fast it reacts with other species like the SOX family that I said earlier, to form the secondary organic aerosols and other pollutant species. So this decreased chemical loss and increased soil temperatures. When we go into the EU, that is European Union part, we find that the rate is a little lesser, 1.83, and here the reason is very interesting. It is actually due to decreased scavenging by acid aerosols. Why is it so? We know that means in Europe the vehicular and industrial restrictions are very severe. Means you know that every few years new emission regulations come, like we had a few years ago a BS4 stage engine. Nowadays BS5 stage engine is also out of the market, and we have BS6 stage engine. So what this means, BS6, BS5, they actually conform to certain emission regulations. That means there are certain criteria that a certain engine cannot emit a certain concentration, means beyond a certain concentration, pollutants beyond a certain concentration. Now this particular restriction is very, very severe in Europe for both industrial as well as vehicular emissions. As a result, what happens is that the SOX and NOx families that is going into the atmosphere, their concentration is decreasing, and they are actually a very efficient sink of ammonia. So by decreasing the sink of ammonia, it is actually increasing the amount of ammonia. The scenario is completely different in China, where it was registered that it is increasing by around 2.3%. Here decreased chemical loss is obviously there, increasing temperature is also there, and increased fertilizer use is also there. The third point is not valid for US and EU. I didn't find much of an information about India except this graph on this paper, in this paper. So I searched and I found that there was one paper, and let me tell you one thing, that there are very small number of papers coming from India which deals with the field studies in atmospheric chemistry, which Dr. Chattopadhyay talked about in the last class, yesterday as well. So we found that this particular work that was done from NPL, Delhi National Physical Laboratory, and published just 6 months ago, it completely dealt with India. Now they said that India is actually registering 1.2% per year growth in ammonia, which may not sound very large, but means there are various other factors as well, which I'm not going to go into right now because of time constraint mainly. And here the major reason is intense agricultural activities and presence of many fertilizer industries. These are the two main reasons. So now you see that if you compare India and China with US and EU, in all four regions ammonia is increasing, but the reason for which ammonia is increasing is different. So if we want to find out a way out from this menace, we need to plan accordingly and not follow them blindly, because our problem is completely different from theirs. So if you look at this, means I will go back to the earlier slide and show you another feature. If you go, means if you look at the US and EU, you find that these two cases, I mean, on the right hand side, these curves actually gives you the seasonal changes. We see that for US on the topmost and the third, this Western Europe or European Union, there is no such sharp peak, because the sources of ammonia is completely different there. In China and India, it's completely like a sharp hill, and the maxima reaches at the very similar time, which is around June and July and August. Why is it so? Because in both these cases, India and China, the major source of ammonia is fertilizer, and the major season for agriculture is the Kharif season, which is around June and July and August. So as a result, if we look at these means MAM, these are actually the initials of the months. So MAM means March, April, May. You see that the ammonia concentration is very high along the Gangetic plains. Then once you move into the JJAS, that means June, July, August and September, which is the Kharif season, then what happens is that this whole region becomes completely burdened with atmospheric ammonia. Once you go into the Rabi season, which is October and November, the situation becomes a little bit better and remains so during the December, January and February months. Another reason we need to remember that this sharp rise and fall is also the temperature. In the whole Gangetic plain, there is a very sharp rise in temperature during the summer months and very sharp fall during the winter months as well. Because unlike Kolkata, where the temperature normally fluctuates between 20 to 40 degrees centigrade, if you go to Kanpur or Allahabad or Amritsar or Jaipur, here where I'm sitting right now, the temperature change is more than 40 degrees centigrade over the course of the year. It can go beyond 46, 47 degrees centigrade in the summer. It can go as low as 3 to 4 degrees centigrade in the winter. So large change in temperature actually changes the volatility of ammonia by a large amount. Okay, so and one more thing that I would like to point out is that the satellite or the imaging system that these NPL people used for studying this seasonal behavior of ammonia on India was a different one. It is IASI, which is infrared atmospheric sounding interferometer, and it is actually stationed in a Met-of satellite launched by the European Space Agency. Normally, if you look at the various satellite data of ammonia over the course of the last 10 or 12 years, you will find that almost all of them, if not all of them, are actually coming from this AIRS and IASI detectors. Now, we have talked about various stories, but we need some numbers before we can start working with. Okay, and so let us look at some numbers that actually matter for our work. We know that ammonia is the most abundant basic gas in Earth's atmosphere. So let us tally it with the most abundant acidic gas, which is formic acid in atmosphere. So the global emission from ammonia ranges from 43 to 80 teragram per year, and this value is much larger compared to the the emission of formic acid, which is 27 to 57 telegram per year. And with increasing time, there has been a very effective and very earnest trial for curbing the emission of formic acid. Unfortunately, we do not know anything of such kind for ammonia, or we cannot do such things right now. The second thing is that what will be the concentration? That is also very important. Now, as I said, that we normally measure abundances in terms of ppbv. So the atmospheric mixing ratio, the volume mixing ratio that we talked about, it ranges from 0.1 to 10 ppbv. That is actually a global average value. And for formic acid, that range is within 0.01 to 10 ppbv. But if we look at the local scenarios, let us suppose if we look at open air cattle feeding facilities, the ammonia emission, or rather the ammonia volume mixing ratio, could be as high as close to 3000 ppb, which is around 300 times greater than the global average. That is very important. That means the local effect of ammonia on atmosphere could be very drastically different from the global effect that we see. So we need to remember the local part as well. And the most important one is that this temperature, that ammonia volatilization potential almost doubles up every 5 degrees centigrade. So now you can actually sense that why there is such a large jump from January to July in ammonia emission in Indian subcontinent, as well as in China, in some parts of China. So all these numbers actually tell a grim story. So let us talk about something that is a little more positive in nature. The major reason for ammonia emission is production of our food, and that actually increases with the growth rate of population. The good news is that over the last 50 years, the population growth rate has declined from 2.2% to 1.05%. So we are not looking into a future as grim as we used to think until now. So now let us go into the atmospheric H atom transfer reactions. Now, if for a chemist, if someone asks that what is the simplest reaction, hydrogen atom transfer could be the answer, because what happens in this case is that this reaction can take place by transfer or migration of a hydrogen atom from one atom center to another atom center. It could be an intermolecular or it could be an intermolecular reaction, but the bare necessity of this reaction is just a movement of a single hydrogen atom. A very classical example is the tautomerization. Various different types of tautomerizations are there, like ketoenol, aminamine, etc. I have shown here the tautomerization of acetaldehyde to vinyl alcohol just because this particular reaction is important from atmospheric chemistry point of view. So if we look at this reaction, effectively you see that this red hydrogen, which was attached to this carbon atom, gets transferred to the oxygen atom, and there is a transition state where the transition state has this hydrogen bound to, loosely bound obviously, to both the carbon as well as the oxygen atom. So means how much important hydrogen atom transfer in atmosphere? if we look at the most important OVOC, or rather most abundant OVOC, OVOC stands for oxygenated volatile organic compounds. Now, that means the organic compounds which are volatile and which have an oxygen, one or more oxygen atoms in them, those compounds are very important from atmospheric point of view. And if we take the most abundant OVOC, then methanol is that one. And if we look at the chemistry of methanol in atmosphere, the major chemistry of methanol in atmosphere is its oxidation to water, ozone, and carbon dioxide. But this oxidation, although the overall reaction is formula is methanol plus oxygen, it is actually initiated by OH radical. OH radical is considered to be one of the most important oxidizing agents in atmosphere, and due to its very high reactivity, it is called a detergent of the atmosphere because it helps clear things up. So you see that the first four reactions, in the first reaction, what happens is that the one methyl hydrogen from methanol goes to OH and becomes H2O. In the second reaction, the second methyl hydrogen goes to the oxygen and becomes hydroperoxyl radical. In the third one, this hydrogen from attached to the oxygen goes to the OH radical once again, and we get this formyl radical. The fourth one, you see that once again, that also involves a transfer of a single hydrogen atom. So if we look at these four reactions, they are actually hydrogen atom transfer reactions or HET reactions. So that gives us some idea that how important the HET reactions are from atmospheric point of view. Now, what are the different types of HET reactions that could happen in atmosphere? There could be an addition reaction like the hydrolysis of formaldehyde to methanethiol, where this formaldehyde reacts with water and the one hydrogen of water goes to the carbonyl oxygen, and this OH group binds to the carbon atom. It could be a rearrangement reaction like we talked about, the tautomerization of acetaldehyde to vinyl alcohol. It could be a fragmentation reaction where this carbonic acid gets dissociated into two parts, which is carbon dioxide and water. Here also you see that it actually involves the transfer of this hydrogen atom from one oxygen to another oxygen or another hydroxyl oxygen. Now let us talk about what ammonia can do in a HET reaction. It actually can participate in a hydrogen atom transfer reaction in two different roles, as a catalyst and also as a reactant. Now, why catalysts are important? Because you see that all these reactions we talked about earlier, they involve a breaking of an XH bond. This X could be carbon, oxygen, or nitrogen. And we know that XH bond is a very strong bond. Its dissociation energy goes into a few tens of kilocalorie. In fact, it's north of 60 kilocalorie or 80 kilocalorie, depending upon what kind of system you are choosing. So obviously you need a large amount of energy to put into the system for these reactions to happen. And as a result, these reactions are very unlikely to happen in Earth's troposphere. I have specifically written here troposphere. I will talk about it later on. Why I have not written atmosphere here and written only troposphere here in a couple of slides only. So why is it unlikely? Because the maximum temperature that we reach in troposphere as well as in stratosphere is around 330 Kelvin. The maximum means noted temperature, and you can very easily find out the Arrhenius expression. What will be the rate constant when you have a barrier of around 40 or 30 kilocalorie, and the reaction is happening at 330 Kelvin temperature? It will be inconsequentially small. The rate constant will be the lifetime of the reaction will be maybe millions of years. Okay, or maybe even larger than the age of the Earth. If you calculate it, you will find. So what happens is that the bifunctional catalysts come into the rescue mission. what they do is that they get attached to this hydrogen. We call them bifunctional because they actually act as two different, act as hydrogen acceptor from one part and hydrogen donor from one part. So a very easy way to recognize a bifunctional catalyst is that they will have an electronegative atom on them which has lone pairs of electrons on it, which can accept a hydrogen atom and becomes a conjugate acid. That means if you take a HX, it becomes H2X plus kind of a situation. And it can also have a H atom bound to an electronegative atom like oxygen or nitrogen or fluorine, which it can very easily give away because of its high acidity, and becomes its conjugate base like X minus. When it acts as a catalyst in HAT transfer reactions, hydrogen atom transfer reactions, sorry, it acts as both the proton acceptor and proton donor, as shown in the lower graph. So here, this red hydrogen is part of the reactant molecule, and this blue hydrogen is part of the catalyst molecule. When it forms a pre-reactive complex before the start of the reaction, the unimolecular transformation, it gets hydrogen bonded and forms this kind of adduct. And then during the TS, where the TS involved transfer of a single hydrogen atom in uncatalyzed reaction in the upper figure scheme, here you see that the TS involves simultaneous transfer of two hydrogen atoms. This double proton transfer or double hydrogen transfer, atom transfer, actually reduces the barrier by a large amount. We will see how efficient they are. But this is a very well-known experiment, and there has been plethora of works on the efficiency of catalysts bringing down reaction barriers. Now, what are the different conditions that needs to be satisfied for our catalyst to be efficient under atmospheric conditions? We know that the rate of a reaction and nth order reaction depends on two factors: the rate coefficient and the concentration of the various species that is participating in the reaction. So obviously, the larger the amount of catalyst in atmosphere, the larger will be the rate, provided the rate constants are same. Then we know that this rate constant depends on two different parameters. One is something which is known as the energy of activation, which normally we call about the energy of transition state compared to the energy of the pre-reactive complex. And the second one is the temperature. So obviously the catalyst should be able to efficiently bring down the barrier to a very low level so that the reaction can happen at an ambient temperature near 300 Kelvin. And this temperature, obviously it has its own importance from kinetic point of view, but it has a very important, very large importance from atmospheric point of view as well. Because when we talk about various reactions, we do not talk about the reaction under a certain condition. In atmosphere, conditions vary with season, with geography, with altitude, and we'll talk about this also in the coming slide. So if we look at the work that has been done in the last 10 or 15 years, we find that the most of the works, this particular work came in 2016, this account of chemical research, which kind of gave a perspective of the research work done in the field of double hydrogen atom transfer reactions in atmospheric chemistry. They actually talked about the catalysts in details, and they specifically said that atmospheric acids and water typically mediate these reactions. They specifically said that atmospheric acids and water, and when they said atmospheric acids, they included organic acids like formic acid, acetic acid, so on, as well as inorganic acids like H2SO4, HNO3, and so on. So our question was, why not ammonia? Because ammonia can act as a bifunctional catalyst. Ammonia is present in the atmosphere in sufficiently large amount, obviously in trace amount, but when you consider the various trace species, ammonia is sufficiently, means it is actually present in atmosphere in higher abundance compared to formic acid. And the future projections indicate that it is not going to be coming down in the near future. We do not know a way to get it down. So why not ammonia? But before we go into that, let us get back to this temperature part and the altitude part. If we look at our atmosphere, we see that temperature is a very important parameter in atmosphere. How important it is? When we layerify different parts of the atmosphere, like troposphere, you all know that troposphere, stratosphere, mesosphere, and thermosphere. How do we segment these layers? It is actually the temperature. When we go from troposphere to stratosphere, the temperature gradient actually changes. In fact, it gets inverted. So when we are in the troposphere, the temperature gradient is negative, that is, temperature decreases with increasing altitude. When we go into the stratosphere, it is opposite, that means temperature increases with increasing altitude. In mesosphere, it becomes opposite. Thermosphere, it becomes once again opposite, which is the same for the stratosphere. And the region where this gradient change takes place, we say that this is the boundary of these two layers. So tropopause means that when the gradient of temperature becomes positive from negative, that particular range is known as tropopause. Now, why temperature is so important from atmospheric point of view? Because of two reasons. When we are talking about atmospheric chemistry, mostly 99% of time, we are interested in troposphere and stratosphere. You will find hardly any work on mesosphere and thermosphere, mainly because of two reasons. We are very much shielded from them because of the stratosphere, and we haven't yet devised a way to destroy the mesosphere. We have been able to destroy only up to stratosphere to some extent. Okay. Now, the stratosphere and this troposphere have a completely opposite nature, and those opposite nature is mainly because of this temperature gradient, or the opposite nature of the temperature gradient. In troposphere, you have a negative temperature gradient. That means that can be very easily correlated with a kettle of water on the oven. So you are heating it from the bottom, so troposphere gets heated up from the surface of the earth, not from the direct sunlight. And as a result, the turbulence that we see in a kettle, when the water gets boiled, we see similar kind of turbulence in troposphere. And that's what actually helps us to live, because without that turbulence, we will not have airflow, we will not have rain, we will not have different climates and all these things. And we will not have removal of these pollutants from the troposphere, either by dry deposition or wet deposition. In the stratosphere, the situation is opposite. Its name actually suggests that it is stratified or layerified. It has a very stable and well-organized layers, like the ozone layer that Dr. Chattopadhyay talked about in the last day. So what happens is that in this case, as the temperature becomes higher with increasing altitude, there is no turbulence. The advantage is that it helps keep the ozone layer intact until and unless perturbed with what we have done with CFCs. And but the problem is that this ozone layer is there, there is no perturbation. But what happens is that if you send something into the stratosphere, that is also going to reside there for a long time. Unlike troposphere, where the dry and wet deposition can remove the pollutant within a few hours or few days or weeks or at the most months, in stratosphere, it will be sitting there for decades. And in last lecture, Dr. Chattopadhyay showed that how, in spite of stopping the production of CFCs, how CFC is still there in the troposphere in large amount. So what happens is that once some pollutant species goes into the stratosphere, it stays there and keeps on doing showing its harmful effect for a very long time. So that's why you see that when we are talking about atmospheric chemistry, temperature is a very important part. Now, coming back to the thing that ammonia, we have talked about the catalyst. Ammonia can act as a reactant as well. How? A very common atmospheric HET reaction that we know of is addition of water, normally in atmospheric chemistry field known as hydrolysis reaction. And we find that almost all the acids, or rather I will say specifically inorganic acids that are present in atmosphere, are the result of hydrolysis reaction. Like H2SO4 results from hydrolysis of SO3, HNO3 in during the night time, during when sunlight is absent, results from hydrolysis of N2O5, and so on and so forth. So ammonia and water are very, very similar in nature from their chemical point of view and from their structural point of view as well, from their electronic structures as well. So we can think of that if we replace the water with an ammonia, like what we have done in this case, that if we replace the water with ammonia, what will happen is that in case of hydrolysis, this reaction takes place like this water splits, one hydrogen goes to one of the oxygens, and this OH gets attached to one of the nitrogens. Similarly, in this case, one of the hydrogens will get attached to one of the oxygens, and this nitrogen with its two hydrogens, that is the amine, will attach to one of the nitrogens, and the result will be one. Means in this case we have two molecules of HNO3. In this case we will have one molecule of HNO3 and one molecule of nitroamine. Sorry. So now before going to the work, let us look at how this work is done. If we see what we are looking for, we find that we are actually looking, means our major goal is to find out what is the reaction rate coefficient. Normally what we do is that we use various different types of models or methods for calculating the reaction rate. The easiest of them is transition state theory that we use. Then we use a variation of transition state theory known as variational transition state theory, and we use master equation based RRKM method. RRKM stands for Rice, Ramsperger, Kessel, and Marcus, the four scientists who developed this method. Now, for calculating these rate constants, the requirements is that we need to know some external conditions like temperature, pressure, the nature of the collider gas, what is the energy of the collider gas, all these things, and some molecular specifications like geometry, energy, vibrational frequencies, etc. Now, if we look at this particular graph, this reaction profile, we see that the various different species that involves in a reaction, they are characteristically very different. Very different species are there. One is the reactants or the reactive complexes, which are a minima on the potential energy surface. That means if you start from the equilibrium geometry and go in any direction along any vibrational mode of the molecule, you will find uphill. On the other hand, you have a different type of species which is known as transition state, and it is unique in nature in the fact that on the potential energy surface, this is not a minima as such, but it is known as a saddle point of first order. Now, what is a saddle point? Saddle point means that this particular point on the potential energy surface is minima along certain directions and maxima along certain directions. If a particular saddle point has a maxima along only one direction, this is called a first order saddle point, and transition states are characterized by first order saddle points. There have been some works in the recent past on reactions going via second order saddle points, but we are not going to move into that regime. We will confine ourselves in the first order saddle points. Now, question is, when we do the calculations, how do we find out whether this particular geometry that I have gotten is a stationary point or is a transition state? And here I would like to quote from a book named The Spectra and Dynamics of Diatomic Molecules, which actually gives the essence of all the words that we give. It goes on to say that insights into the structure of molecules and their reactivities have been, for many centuries, gained by imagining the molecule to be a tumbling network of springs. Exactly, we do all these things by considering the bonds as springs. And when we talk about springs, the first equation that comes into our mind is the Hooke's law, which is obviously a very crude approximation, provided the spring is not oscillating by a large amplitude, but the amplitude is very small. But this expression gives us the potential as, finally, the potential as half of kx square. Now the problem is, now if we solve the Schrodinger equation using this potential, we get the frequency as 1 over 2 pi root over k by mu. This k we know as the force constant of the bond. The stronger the bond, the harder the spring to elongate or compress. The weaker the bond, the easier it is. Now question is that if we look into the Hookean force, it gives us something called a harmonic oscillator, and this harmonic oscillator is actually you cannot break it. It is infinite, means this potential wall is infinite. But we know that for a reaction to happen, a bond needs to break. So how come an infinite wall which doesn't allow bonds to break means be used to study reactions? That sounds difficult, but this harmonic oscillator model actually serves our purpose, because if we concentrate on the lower part of the potential energy surface, that means between this near this ground state, this first excited and so on, we see that the deviation of the original curve or original potential energy surface from the harmonic potential energy surface is very small. And when we are talking about normal reactions, thermal reactions, the temperature at around 300 Kelvin if you take, and if you calculate the probability of finding a molecule in V is equal to 1 for a vibration, let us say OH vibration, which is around 3500 centimeter inverse, you will find that the probability of finding the molecule in the first excited state, even in the first excited, is very small. So effectively, we are talking about molecules which are predominantly sitting in the ground vibrational state, and to some extent, provided the for weaker vibrations, to some extent in the first excited state. So using this actually works. Now, if we look beyond the Hooke's theorem, we see that in reality, this Vx can be expressed as a Taylor series expansion. It is not having a very fixed kind of scenario like half kx square. And if our what we have talked about here, if the total oscillation or amplitude of the oscillation is not very large, then what happens is that the larger terms, this n is equal to when n becomes very large, their contribution becomes negligibly small. So we can truncate the series. Now, when we truncate the series after the third term, we have this v at xe, and the first derivative when x is equal to xe, and the second derivative. And we know that this particular term is a constant, so we can always scale it to 0. This particular term, that is the first derivative, it is also 0 because we are sitting at the minima of the curve, and we know that the first derivative of the curve is minimum, is 0 at the minimum, and we are left with only the second derivative. So effectively, Vx comes out to be half of d2v dx2 at x is equal to xe into x square, and if we try to tally it with this equation, we see that this this k, which we talk about as force constant, is actually the second derivative of the potential with respect to the coordinate. And the second derivative gives us the curvature. So the higher the curvature, the stronger the bond. That means to elongate it by the same amount, you need higher energy. So as a result, this new value becomes larger. Now what we do is during the calculation is that first of all, we calculate the first derivative, make it 0 in an iterative manner. And when we reach 0, that signifies that we have reached an extremum on the potential surface. But from this value, we cannot say whether this extremum is a minimum or a maximum. For that, we need to find out the second derivative. When we calculate the second derivative and find out that the second derivative becomes positive, we know that we have reached a stationary point. That means it is a minima along all the directions or all the normal modes of vibration, resulting that this d2v dx2, as this is connected to k and this k is connected to nu, that means nu is proportional to root over k. So what happens is that if this value is positive, k is positive and nu is real. So a very easy way to determine whether we have reached a stationary point or not is just to look at the vibrational frequencies, and if all the vibrational frequencies are real, then it is indeed a minimum. If, however, this value is less than 0, that means negative, it signifies that we have reached a maximum. So to get a transition state, what we need is that we need a point where the molecule or the system is in a point on the potential energy surface which is minimum along all the directions, except the one direction which results in the reaction. And that particular mode, which is known as the reactive mode or reaction mode, will have an imaginary frequency, because this d2v dx2 is negative, which signifies k is negative, and root over k results in a imaginary frequency. That's how we do it in a nutshell. So what is the way we calculate these things? First of all, we do a geometry optimization plus the frequency calculation, as we have talked about right now. Then normally this geometry optimization is carried out in a comparatively lower level, and we need the energy values to a very high precision. So what we do is that we do single point energy calculation later on at higher levels. In certain cases, certain very specific cases, we need to do post CCSDT calculations, specifically for systems where you have multi-difference character like radicals or ions, and some certain molecules like ozone and Greek intermediates, which are not radical or ion but still have very high multi-difference character. Oxygen, obviously. Then we do the rate constant calculation. What we do is that for geometry optimization, we normally use DFT method, MP2 method, and QCSD method. In some cases, for this, we use Gaussian and GAMES. Out of this, GAMES is completely free of cost. ORCA is also free of cost, which is used for CCSDT FQL calculations. Then single point energy calculations are carried out in CCSDT FQL, which uses ORCA, and CCSDT calculations, which uses Gaussian or GAMES, which we use. Then post CCSD calculations are used done mostly using MRCC codes. And finally, rate constant calculations are used. We use TST, that is transition state theory, variational TST, master equation, RRKM theory. And for TST, we can use the R8 and key statement. There are several various different softwares available. In fact, students can try writing the code in Fortran or C. That is actually can be a part of a project as well. Then you have this VTST, which we normally use polyrate for calculation purpose, and for the master equation based methods we normally use multi-well and Mesmer. In between them, for single point calculations, we sometimes do CBS extrapolation to get the artifacts introduced by the basis sets. And for rate constant calculation, tunneling is an important part, because we are talking about hydrogen atom transfer, and hydrogen atom transfer, hydrogen being the lightest element, the tunneling probability is highest for it. So we use different models for tunneling like ECART, ZCT, SCT, and so on. Now this is specifically, I actually talked about this particular part in great details, and I think many of you have been feeling very bored, but I did this mainly because there are around 50% of the registered participants are undergraduate students. So what I will do is that I will tell you that if you are interested, you can go through these books. One is this Computational Chemistry by Errol Lewis. This book, if you want to read in free, the important chapter that is on the potential energy, or on the concept of potential energies, it is available in Google Book Review. So you can go and read the whole chapter. Only the reference part you will not see there. And the second book that wherever there is a chemistry department, you cannot think of one without this book. This is Quantum Chemistry by I.N. Levine. In 7th edition, the chapter number 15 and 16, this molecular electronic structure and electron correlation methods. Whatever I talked about in this part, this BFT, MP2, PCISD, and various different basis sets that I am going to talk about later on during my work, they are available here in a very simple, lucid manner. So once you know what perturbation theory and variational principle is, you can actually go into these chapters and read it on your own. Okay, so now means getting into the words, I would like to request the moderator to let me know how much time do I have. Do I have any time at all? Okay, let's continue. I hope he will stop me when the time is over. That's what moderators should do. Anyway, so first thing we are going to talk about is ammonia as catalyst. I'm going to move along this path in a little faster manner. So decomposition of carbonic acid was the first problem that we chose to work on because it had been obviously decomposition of carbonic acid is not a very important phenomenon from Earth's atmospheric point of view. At H2CO3 is available in gaseous form in other atmospheres, planetary atmospheres, but in Earth's atmosphere it is not a very important trace species. But we, as it was our first work and we tried to standardize our method, we chose one problem which was well studied. And just a year ago, we started working. The group of Professor Montu Hajra from SINP, they studied in great details in this paper about the various different catalysts on the outcome of this reaction under atmospheric conditions. But all the catalysts that were studied until our work was basic or water. Sorry, or either acidic or water. Pardon me. Now, they found that at around 0 kilometer altitude, that means at a very low altitude, close to the surface of the Earth, H2O, that is water dimer, and formic acid catalyzed reactions are of very similar importance. You cannot neglect any of them. We tried to know that whether we can neglect ammonia as well. So we did the geometry optimization. These are the geometries for uncatalyzed, water catalyzed, and water dimer catalyzed. We did this calculation in MP2 oxy-CpPtZ and then did the single point energy calculations in CCSDT oxy-CpPtZ and found out that the potential energy surface showed that the barrier is around 40 kilocalorie uncatalyzed reaction, which comes down to 16.6 kilocalorie in presence of a water and comes down to 8.4 kilocalorie in presence of a water dimer. We devised the mechanism. This mechanism says that we have this H2CO3 reacts with the X, which is the catalyst, and we assumed that they are actually this RC. This is the p-reactive complex. This p-reactive complex is in equilibrium with the isolated reactants, and then this RC goes via TS and forms the pre-product complex PC, and that rate is given by K2. Now, if we consider this RC and these isolated reactants in equilibrium, then the rate constant can be written as this K equilibrium into K2, where K equilibrium is K1 by K minus 1. This is very simple, and it really works for this problem. But there are certain other problems that we are going to talk about later on. So, by using TST, the expressions are this, that K equilibrium and K2. These are very much available equation. You can go to Ledler's book and you will get all these derivations. It is actually taught in the BSc as well, I think. So we get the rate constant as for water monomer catalyzed reaction. It was minus 25 of the order of minus 25 centimeter cube molecular unit per second inverse. For the water dimer case, it was around 3 times 10 to the power 3 times faster. So we looked at ammonia as well as ammonia dimer, and we found that for ammonia the barrier was around 10 kilocalorie. For ammonia dimer the barrier was very small, around 1.8 kilocalorie, and the rate constants were significantly higher. For ammonia, it was around 10 to the minus 21, and for ammonia dimer, it was around 10 to the minus 18. So, and also we recalculated the formic acid catalyzed at our own level, and we found that its barrier was around 3.4 kilocalorie, and its rate constant is around 10 to the minus 17 centimeter inverse. So if we just tally the rate constant, we find that this formic acid having a rate constant of 10 to the minus 17 centimeter inverse, and it is actually the fastest reaction in terms of rate coefficients. But as we have talked about, that rate coefficient doesn't give you the full picture. You need to look into the rate constant, the overall rate of the reaction. So what we do is that we calculated the effective rate constant, which is nothing but the pseudo first order rate coefficient. So you multiply the catalyst concentration with the bimolecular rate constant, and this expression captures the combined effect of the catalyst concentration as well as the reaction rate coefficient. And if when we calculated all these things, considering the lower and higher limit of various different catalysts present in Earth's atmosphere at 0 kilometer altitude, obviously, we find that the K effective value, the higher limit, changed from 10 to the minus 8 to 10 to the minus 6. The maximum was for 10 to the minus 6. And for ammonia, obviously, the value was very small, minus 10 to the minus 11, when we talked about the global average. But when we took the local average, that 2900 ppb value, it actually becomes 3 into 10 to the minus 7, which was comparable, in fact, better than the water monomer and dimer, and very much comparable to formic acid. So what we can do is, what we can say is that you cannot neglect ammonia. There could be certain reactions where ammonia can result in a significant amount of loss mechanism. So next, what we did is that now a little bit of discussion is needed for this rate coefficient. What we did in this case is that we used a steady state approximation for the rate calculation, and steady state approximation applies. If you apply, the rate coefficient becomes this, that K1 by K minus 1 plus K2 into K2. Now you see that we used a rate coefficient which is K1 by K minus 1 in K2. This particular expression, means obtaining this expression from this one, requires us to approximate or assume that this RC is in equilibrium with the isolated reactants. Now you can always do this assumption when the RC is only slightly stabler compared to the isolated reactants, but the TS is very high in energy. What happens is that in that case, the K minus 1, which is this rate, that is the formation of A plus X from RC, that is the by dissociation reaction, this rate is much faster than the rate of conversion of RC into TS and PC. Now, if that condition is satisfied, that means the potential energy surface looks like this, then obviously K minus 1 is much larger than K2, and we can very easily say that this reaction can be approximated to this reaction without significant overestimation of the result. Overestimation because you are actually subtracting one part or removing one part from the denominator. So obviously it will overestimate the reaction. Now there are reactions we will see in the atmosphere which have a potential energy surface like this, where the TS is deeply buried. Effectively, the reaction is overall reaction is barrierless. That means the TS's energy is lesser than the overall energy of the isolated reactants. Now, in this case, this K minus 1 is not very small, it's not very high, it is small. Rather, this K2, that means the conversion of RC to PC via TS, it is large. And in this case, when this K minus 1 is either small or very close to K2, you cannot simply neglect this part, K2 part. You are simply making this denominator half or even lesser. So effectively, you are overestimating the reaction rate coefficient by a large amount. The question is, when that happens, what should we do? So let us discuss the next problem and find out what we can do for that. The next problem that we chose is the sulfuric acid formation. This is a very important problem from India's point of view as well, because we use a lot of lignite coal which has a large amount of sulfur. in power stations and brick fields and various different other purposes. So the amount of SOx as a result is very high. So SO3 can react with water, it is shown here, and form H2SO4. Okay, now the role of ammonia in the chemistry of SOx and H2SO4, there has been a lot of work on this, but those works have been mostly concerned on the secondary organic aerosols, where ammonia comes and reacts with H2SO4, forms the NH4HSO4 and neutralizes it. What we are saying is that if ammonia can catalyze this reaction, it will help in formation of H2SO4, which might sound intuitive in nature, because normally we know that bases are more prone to normalizing or neutralizing acids. But here what we are saying is that a base could actually result in a more amount of acid in the atmosphere. So let us see what happens. This particular problem is a very long problem, but initially people found that this reaction, just like the other hydrogen atom transfer reaction, involves a very high barrier around 30 kilocalorie per mole. But in 1994, Morokuma and Muruguma in their seminal paper showed that, this is one of the most interesting paper from atmospheric point of view. It actually showed that if you add one water into the system, which acts as a catalyst, the barrier comes down by a large amount, and later on various different groups actually showed that this barrier is within the 6.5 to 13 kilocalorie per mole. Now there has been, obviously, when water came into the picture, people started working with various different catalysts, and obviously acid catalysts took the center stage, and people found that HNO3 catalyzed reaction showed a barrier of around 5.5, H2SO4 around 1.4, and HCO2H, that is formic acid, almost showed a barrierless reaction. Then, based on the work Jordan Sikurat in their paper in 2012 said that in troposphere, water catalyzed hydrolysis would dominate mostly, because water concentration is very high here and H2SO4 concentration is much lower. But in stratosphere, where water concentration is much lower, temperature is much lower compared to the lower troposphere, the H2SO4 catalyzed hydrolysis would dominate in stratosphere. There has been a very interesting paper by Professor Hajra's group in SINP on the opposing process in stratosphere. One might be, someone, if someone is interested, you can go in and look for the paper as well. It came in Chemistry Communications from Nature Group in 2019, which is open source paper. Anyway, coming back to the topic. So our focus will be obviously in troposphere, because not much is known about ammonia in stratosphere. And honestly speaking, not much is known about the ammonia or its state or its abundance in higher troposphere as well. Okay, so now we are actually in a different regime. In carbonic acid decomposition, we had a two-body reaction, that is a bimolecular reaction. Here we have three-body reaction. You have a SO3, you have a water, and you have a catalyst, which could be an H2O or some other molecule. So three-body collision, but three-body collisions are very rare in atmosphere, because if you think of these species, they are all present in ppBV volume. The temperature is not very high. The density of air is also very small. So as a result, you cannot think of three-body collisions. So normally what happens is that these reactions proceed in a sequential bimolecular process. That means initially, let us suppose we have a reaction like A plus B plus X. So initially, any two of these collides and forms a weak complex, and there are three possibilities: AB, AX, and BX. And then it has a lifetime of its own. During this lifetime, which is much larger than the possibility of a three-body collision, the third body, which is X in this case or B or A in these cases, can come and collide and form the RC, which goes via PC to the final product. Now, in case of water catalyzed hydrolysis, we have two different channels, because in this case B and X are same. So you cannot have 3 different channels. For ammonia catalyzed hydrolysis also, we have only 2 different channels. What happens is that if we look at this AB channel, if it goes via, if it goes via AX, that is A is SO3 and X is NH3, then when SO3 binds with NH3, there is a bond between the sulfur and nitrogen. So as such, you cannot have sulfuric acid from that molecule. You will actually eventually get sulfamic acid, which will result in a completely different reaction, which we are not interested right now. So we have two channels each for these 2 reactions. So if we look at these 2 reactions, we find that the potential energy surface, which was calculated at this level, looks like this, and in both the cases, the TS you find is buried deeply inside the isolated reactance energy. So obviously what happened is that when we calculated the rate constant, we find that the water catalyzed rate constant was 1.1 10⁻², which was very close to the experimental rate constant, but the ammonia catalyzed rate constant was very high. It was 8.9 into 10⁻5. This rate constant is much higher to the gas kinetic limit. Now, obviously, question could arise: what is gas kinetic limit? If we consider any reaction, the most primitive or most easy theory that we can devise is a collision theory, which tells that the reaction rate is a multiplication of 2 different factors. One is that how fast or how frequent the molecular collisions is taking place, and a factor which tells you what fraction of those collisions have the energy to cross the barrier of the transition state or the activation energy. Now, if we consider that all the collisions result in reaction, that means there is no barrier as such. Whenever a 2 molecules come into one another's contact, they react. Then we are going to have an upper limit of the rate coefficient. Now, under atmospheric condition, for this stress species, this upper limit has been found to be around 10⁻⁹ to 10⁻10 molecules per centimeter. 10 molecules per centimeter cube, molecular unit per second. So obviously, this particular value is actually overestimating the rate coefficient by at least 5 order of magnitude. And if we look at this value, which matches with the experiment very closely, we need to be a little bit skeptical about our findings and need to ask ourselves that whether this single matching, is it systematic or accidental? And here comes the importance of the temperature. So let us look into the this matching part. What we find is that if we plot the temperature dependent rate constant starting from 320 Kelvin, which is at this end, to 213 Kelvin, the whole temperature range encountered in the troposphere, we find that the water catalyzed hydrolysis channels, they actually show a large amount of deviation or temperature dependence. In fact, the value that was 3.4 into 10⁻11 at 320 Kelvin became 6.9 minus 10 to the power 8 centimeter at 213 Kelvin. Now, just imagine if your reaction is fast enough to be at the close of the upper limit, how it can go even higher in value. Means you can have one product from one collision. You cannot have 3 products from one collision in any way. Nah? So obviously, if you look at the temperature dependence, it actually shows that this matching that we saw for the water catalyzed channel is not a systematic matching, but it was an accidental matching. We should look into it in more details. So we know that these very fast reactions show a negligibly small temperature dependence. So what we did is that we went and found out the calculated the rate constant using energy grain mustard equation. In this case, what we do is that we take the barrierless association process and we treat it using inverse Laplace transformation, and the step involving the activation energy, we treat it using RRKM expression. Okay, and then we calculate the microcanonical rate constant, that is K of E as a function of E. It is not the canonical rate constant like what we get in TST or VTST, which is rate constant as a function of temperature. So I'm not going into the details of this anyway. So what we what we found out is that we found the most important thing that I missed out is that here no assumptions are made beyond assuming the validity of the statistical rate theory. That means the assumptions that are incorporated in this RRKM expression, that is the only assumption. We are not assuming, we are not making any approximation that how this this RC and this isolated reactant is linked together, whether there is any equilibrium existing or not. Okay. So what we found out is that if we look at the hydrogen H2O catalyzed reaction at 213 and 320 Kelvin, the rate coefficients that we found out using this master equation, which is given in this black color code, bold black color, they are -12 and -13. So effectively there is a change of only around 1 order of magnitude, and both these values are below the gas kinetic limit. On the other hand, in TST we have gotten this -11 and -8. For NH3 catalyzed, where the situation was very severe, when we had gotten this 10 to the -5 for 213 Kelvin, and for 300 Kelvin 10 to the I'm sorry, I have made a mistake here. Actually, it is 213 at 5.8, means 5.8 will be actually at 213, and 1.3 into 10 to the -5 is actually at 320. Because if you look at the temperature profile, the rate coefficient is high at lower temperature, rate coefficient is low at higher temperature. It is actually shows a negative temperature gradient. Now you see that as this reaction rate is very close to the gas kinetic limit, there is hardly any change in its value over the course of 100 Kelvin temperature, which is expected. So master equation method actually helps us getting a good result for this kind of low barrier reactions. Now, last part that I am going into is that ammonia as a reactant. For this process, we chose a certain problem, which is amides in atmosphere. Now, amides is important because it is present in significant trace amount, ranging from 0.1 ppdv to few ppdv. Means C3 amide is available at 8.7 ppdv, to be more precise. Now, amides sources are primary and secondary. Primary means that amide as such goes into the atmosphere via biomass and fossil fuel burning and vehicular exhaust. And the secondary sources, which involves that some other species goes into the atmosphere and gets converted into acetamide. I will take just 5 more minutes. Okay, 5 to 7 more minutes. Secondary source is the one where some other species goes into the atmosphere and reacts and forms the particular amide. Like here, we find that amines can go into the atmosphere and undergoes oxidation initiated by OH radical and forms amide. The third possibility that was proposed by Barsanti and Pankov in 2016 is that there could be accretion reaction where organic acids could react with ammonia and amines and form a CN bond in the atmosphere and form amides. Then in 2013, Veronica Vaida's group actually experimentally showed that it means other than acids, ketene can actually act as a very good source of acetaldehyde under atmospheric condition. So ketene, when it reacts with water, can result in acetic acid. So we just simply replace the water with ammonia, and we found that this reaction, if it happens, will result in acetamide. Now the question that needs to be asked is that what will be the rate constant and how it will fare against this competing reaction with water, especially when water concentration is much larger than the ammonia concentration by around 10 to the 7 to 8 order of magnitude. So the reaction could actually take place via 2 different modes. One is the water could add at the CC bond or CO bond, and the CC bond, it is a single step process where it involves a single TS. For the CO bond, it is a 2-step process where it involves an intermediate, which is a diol, and finally forms the acetic acid. Similarly, ammonolysis also goes via similar kind of reactions in two different parts. One is the addition at CC bond, one is the addition at CO bond, and the mechanism is very similar. If we look at the energetics, we find that energetics are also very similar for the CC bond addition, but for the CO bond addition, the blue lines are for ammonolysis, the red lines are for the hydrolysis. We see that ammonolysis reaction is significantly lower energetic than the hydrolysis reaction. So we calculated the rate constant for these single step reaction using the pre-equilibrium approximation, and for the two-step reaction using a steady state approximation for this intermediate, and found that the rate constant, total rate constant, which is the sum of this KCC and KCO, that is the CO addition and CC addition, and the total rate constant was found to be around 10 to the power minus 39 centimeter cube molecular inverse second inverse for the hydrolysis process. The ammonolysis process was found to be around 10 to the power minus 32. So ammonolysis is around 10 to the power 7 times faster over hydrolysis, and ammonia is around 10 to the power 7 times less abundant compared to water. So if we find out the rate constant, they are expected to be very similar. Sorry, the overall rate. So now if we look at the temperature dependence, we find that when the temperature is decreased, this graph, this is actually the graph, this green graph means represents the total rate constant for the ammonolysis. This graph, the third one among these three, is the total rate constant for the hydrolysis. This cap actually becomes a little larger when we go from higher temperature to the lower temperature. Okay, so as I have shown here the values at 298 Kelvin, we can expect this 10 to the power 7 value will be even larger at lower temperature, that means at higher altitude. Let us see what happens. So what we did is that we actually calculated the relative rate, that means the rate of ammonolysis by the rate of hydrolysis, and this value is the ratio of the rate constant multiplied by the ratio of the ammonia and water. And we plotted the logarithmic curve, natural logarithm, and then on the curve, this horizontal dashed line along 0 is the value that signifies that both the rates are same. That means relative rate is 0, relative rate is 1. That's why the ln value is 0. So anything lying above this line means that ammonolysis is dominating. Anything below the line means that hydrolysis is dominating. And we see that when ammonia concentration is around 209 to 2900, that is on the local scale, ammonia is heavily dominating over the hydrolysis. When ammonia is in its higher limit of global average, that is 10 ppb amount, then irrespective of the relative humidity, this RH stands for relative humidity, here it is 20%, here it is 100%, ammonolysis mostly dominates over hydrolysis. So in an essence, what I can say is that you cannot neglect ammonolysis of ketone and only consider hydrolysis of ketone and say that I have gotten all the loss channels of ketene. So then what we do it is that we found out what is the altitude dependence, and this altitude dependence mainly depends on three factors: temperature, rate constant, and concentration. So with increasing altitude, that means if we go from 0 to 15 kilometer altitude by 5 kilometer increment, the temperature goes from 298 to 259 to 213. So that's a large change in temperature. This is average temperature. The concentration, the average concentrations given in molecules per centimeter cube, you see that water concentration decreases by 4 order of magnitude. On the other hand, it is actually more than 4 order of magnitude. It is around 5 order of magnitude, because here it is 7.7, here it is only 2. So it is 3 into 4 order of magnitude. Here for ammonia we have 2.5 into 10 to the 11, and it goes to 10 to the 8, so it is 3 order of magnitude. So the relative concentration is actually increasing by 1 order of magnitude. and that is effective. That is evident from these values that the relative rate, which was at 0 kilometer altitude, was 3, becomes 19 at 5, 36 at 10, and when we go to the 15 kilometer altitude, it becomes more than 2000. That means if ketene are available at 15 kilometer altitude, then it will prefer heavily undergoing ammonolysis and would not undergo hydrolysis at all, in all practical manner. So in summary, what I can say is that we have talked about the abundance of ammonia and how this abundance signifies its importance in atmospheric chemistry, especially gas-phase reactions. In this case, it was found to be an efficient catalyst for decomposition of carbonic acid, and then we applied it for H2SO4 and found out that in spite of its basic nature, it could actually help formation of H2SO4 in atmosphere and acid. And finally, we found that a reaction of ammonia with ketene could be an alternative potential secondary source of amide in Earth's atmosphere. Before stopping, I would like what Dr. Chattopadhyay said in the yesterday, that there are very few and selected chances in places where atmospheric chemistry research and, more importantly, atmospheric chemistry courses are run, and I have listed some of them inside India. Two of the most important were Center of Atmospheric Sciences in IIT Delhi and Center for Atmospheric and Oceanic Sciences in IISc Bangalore. Then there is one center named Environmental Science and Biomedical Meteorology Division in National Physical Laboratory. They also do good amount of atmospheric chemistry or atmospheric science, as such, not as atmospheric chemistry as such. Then we have our Marine and Atmospheric Science Department in IIRS, which is a part of ISRO in Dehradun. Talking about universities, in my vicinity, we have a Department of Atmospheric Science in Central University of Rajasthan at Ajmer. And for you people, you have a newly built center, not so newly, obviously, in University of Calcutta as well. Finally, I would like to acknowledge Dr. Partho Vishwas, who was during that time was in Scottish Church College, with whom I started working on atmospheric chemistry, and he was one of the reasons I started working on atmospheric chemistry. Dr. Pradeep Kumar, who is my colleague also and was my senior during my MSc days, I did an appreciable amount of work with him during our days in MNIT Jaipur. Saptarshi Sarkar and Subhashish Mallik, they are the PhD students. They actually did the works mainly. ACRB DST, I would like to acknowledge for funding the research, and Computer Center MNIT Jaipur for providing the required computational facilities. And thank you all for your kind patience.
Okay, that was a wonderful presentation. Thank you, Professor Bandyopadhyay, for gracing your important work and sharing with us your findings and opinions today. I believe it will leave a profound impact on our audience. We are running behind the schedule, so we'll open the question and answer session shortly. At this moment, we have a distinguished guest at our virtual studio, Professor Tapas Chakraborty from ISS Kolkata. Professor Chakraborty, our speaker was a PhD student under your supervision. We came to know that if you have any question or query, please ask our speaker. Since this is the last day of our seminar, I also want to add that you are one of the very few prominent chemists in our country who are working on the extremely important area of science or atmospheric photochemistry. I request you to add a few words, which I believe will be very motivational to our students to comprise a large section of our audience today.
Yeah, okay, thank you. Biman, so you listen me? Hello, Biman? Biman? Yeah,
I can hear you.
Yeah. Okay, I think Biman, you spoke nicely, but you touched upon too many things. So sometimes that it might have difficulties for the students to follow. but you could have been much more focused. Actually, you have a lot of data. Anyway, that's a general comment, but otherwise you have spoken very nicely. I have a few questions, but although that the time is really short. So first question is that the data that you have presented is mostly calculated data, right? But all this experiment that you have shown that one can study actually in a chamber. So how much data, this experimental data from the chamber studies are available? I think Biman is not audible.
Dr. Bandyopadhyay, you are not audible.
Hello. Hello.
Biman.
Biman, you can hear me? Biman, Professor Biman, you can hear me? Hello.
I can hear everybody now. Am I audible?
Now you are audible.
Yeah,
Okay.
Now
you are audible.
Yes.
Now you are audible.
Okay.
So I
question
think
is-
Professor Tapas.
Yeah, the calculated data that you presented, my question is that how much is available from the chamber studies?
Not much of the data is actually available from the chamber studies. The H2SO4 work that I have shown, the work was done by Jain et al. In 1996. That was actually done in chamber, atmospheric chamber. Weider's work was also carried out in atmospheric chamber. But there are certain problems in following the kinetics of the studies, because many of them are actually very fast reactions. Like if we consider the Kriege reaction, Kriege intermediates reaction, which is of having a rate constant comparable of the sulfuric acid hydrolysis reaction, catalyzation. They are pretty fast, and they need to be done with a laser based experiment.
No, because this particularly this altitude variation, the experiment that you have shown, that where the temperature is very important, temperature as well as concentration.
Exactly. One problem that I would like to pinpoint here is that whenever these kind of experiments are done, mostly these experiments are done at a temperature either or above 280 Kelvin, because gas phase reactions doing it in laboratory at around 220 Kelvin or 30 Kelvin is very difficult. So in those cases, these calculations come in very handy, because in our calculation we can actually simulate what will be the rate constant at upper altitudes, which is not very easy to simulate experimentally in an atmospheric chamber in here. That is very easy from combustion point of view. There has been large amount of data from combustion point of view, but not from the upper altitudes.
Really? Okay. So, Prajay, you want to make any comment on this issue?
Yeah, I mean, my comment would also be, I was also thinking about this point. Yeah, particularly in this kind of problems, we see a lot of theoretical studies, but I'm not. I don't agree with you with the temperature part. Like it's not that tough to do experiments at 220 Kelvin or 230 Kelvin, unless particularly whatever gases you are using, they are volatile. So this would have enough volatility to. But I don't know. So can you comment on that? Why we don't see experiments particularly on these catalytic reactions? I mean, this is very important because.
Doing experiment at 220 Kelvin at this the temperature is not that difficult at all.
That's what I'm saying.
Is also not going to condense. And second thing is that Biman, one more just point that somewhere you mentioned about this involvement of nitrogen pentoxide N2O5 and this ammonia. Yes. But the atmospheric abundance possibility that this nitrogen dioxide will be in this N2O5 form is very little, right?
Yeah, its concentration is not that high.
Yeah.
I actually showed it as a representative example, because I was already going to talk about H2SO4, so I didn't choose that particular reaction to show.
Okay. Yeah, go ahead.
Okay. So I have another comment. So in your second problem, you showed that basically it's a three-body reaction, and your assumption is that first two molecules are colliding and making a complex, and then this complex are reacting with the third molecule. And you also said that it's very important what is the lifetime of that complex, because that will actually dictate whether there is any possibility for it to collide with the third molecule to have the reaction. So this is a very important assumption, and that all of your work is based on this. So is there any experimental data or any idea about that what might be their lifetimes and whether these approximation can be made? So that's
very good question. Now just think about it in a very simple manner. You have water and you have water dimer. So when I'm talking about SO3 hydrolysis water catalyzed, one of the pathway is SO3 reacts with water dimer. And we know that water dimer, whose stabilization energy is very small, around 2 to 3 kilocalorie per mole, is present in atmosphere in 10 to the power 15 order molecules per centimeter cube. Almost
10 to the power
15 molecules per centimeter cube.
Water dimer?
Yes.
Yeah, but it depends on what is the equilibrium constant of the dimerization.
Let me come to the next part. Now, when we talk about ammonia dimer, obviously ammonia dimer is very small. In fact, I calculated ammonia dimer, and under ambient condition, ammonia dimer concentration is of the order of few tens of molecules. But when you go to the ammonia water complex, its concentration we found out could be as high as 10 to the power 8 to 10 to the power 9 molecules per centimeter cube. For SO3 water or SO3 ammonia, we have reported it in our paper. Its concentration is actually around close to 1% of SO3 present in the atmosphere. So obviously they have a very large lifetime. As such, they are in equilibrium with their isolated species.
Okay.
So this reaction, effectively what you can say is that just like A molecule is interacting with B molecule, here A molecule is interacting with AB complex, and this AB complex has a steady state concentration. So that is obviously very much doable. On the other hand, if you think of intermolecular collisions involving three species which have pp concentration, means you can understand that that will be once in a million years event.
Yeah, obviously.
But that was a very good point.
So yeah, I don't have any other questions. So thank you very much for your very nice, and I got motivated. I learned many new facts. So yeah, thank you.
No, I actually made it mainly for the BSc students. That's why it got me.
Yeah, the introduction was fantastic. Thank you.
So
Hello.
Open for question and
Hello.
Hello.
Yes.
If our audience have any questions, they can put it up in the comment section, and it can be automatically retrieved to our studio, and our speaker can address that. But we actually are really running short of time, so if we don't have any questions, then I request our assistant professor, Dr. Asarullah Mullik, to give a formal vote of thanks to our.
Hello everyone.
Ashok, just wait for a second. There is a question here. I see from Manav Mighty. The question is, what will be the change of rate when we go to high altitude troposphere as the temperature changes and hence the toxic effect?
Okay. I didn't get exactly the last part, that the toxic effect, but the first part is a really good, interesting question. The temperature effect could be completely opposite, and it depends on the effective Arrhenius activation energy. Because if you plot the rate coefficients, against temperature, you can have a positive temperature dependence, like when the temperature increases with increasing temperature. In that case, what will happen is that as you keep on going up in the atmosphere, we will find that the rate constant becomes smaller and smaller, which is the case for the ammonolysis reaction, where the barrier is much higher. But in case of hydrolysis of H2SO4, where the barrier is much smaller, we get that the rate constant is almost changing negligibly. So it really doesn't matter whether you are at 0 kilometer altitude or 15 kilometer altitude, the rate constant will be almost similar. And there are certain reactions that we have studied also, which shows negative temperature dependence, where the temperature, where the rate coefficient increases with decreasing temperature. It means as you keep on going upward direction, the rate coefficient will be increasing. The toxic effect, it has various various different aspects. Like certain molecules, when they are toxic in nature, and when they go certain kind of reactions, they become lesser toxic. And there are certain molecules which show completely opposite nature. So like CFC, if you have CFC is not as such very harmful chemical, other than being a greenhouse gas. But once it goes undergoes a reaction and forms the chlorine radical, that has a much higher adverse effect. I will not say exactly toxic effect, adverse effect. So that could actually depend on that.
Okay, thank you, Professor Bandyopadhyay. I'm afraid that we cannot entertain any more questions. So I will request Dr. Mollik to please go ahead formal vote of thanks.
Thank you, Anirman. Thank you, both the speakers. It's really important what we see that there are very few opportunity for us to study atmospheric chemistry. But with this two talk and two speakers nicely elaborate everything and show us that we can. It's never late. We can, and I expect in future our student will take up this atmospheric chemistry as a major course and enlighten it up with all the great things and do the good things for the environments and for the chemistry. And I'd like to thank both the speakers, Aparajito and Professor Biman Bandyopadhyay, for this nice session. And on behalf of the Vidyamandira family, on behalf of the Vidyamandira Chemistry Department, I like to thank both of them. I like to thank Jeet Maharaj and Ramakrishna for helping us with this digital webinar. And obviously, I like to thank our Principal Maharaj and our Vice Principal Maharaj for allowing us to do this session and do this virtual seminar. And last not the least, I'd like to thank all the participants, particularly our students, our young students who are looking for the good opportunity. And I'd like to thank all the participants for this great session. Without them, it would not be completed like this. So I'd like to hand it over this session to Anirman for conclude this session.
Thank you, Ashab. So we have reached almost to the end of the 2-day spanning webinar. Thank you, Professor Bandyopadhyay, and thank you, Professor Chattopadhyay, for excellent presentation. So for the participants, the feedback link will be provided. It will be sent to your email, and when you fill it up and submit it, the certificate will be provided, sent to your email too. So thank you, everyone, and we conclude our 2-day seminar here. Thank you.
Thank you so much.